Hello, Algebra 2! I hope you guys are having an awesome day. Today we are going to go to 2.9, which is extending a little bit our imaginary numbers and our complex numbers. So this question that I start you off with, I'm actually not going to tell you the answer. So I want you to think about it and come to class with, what you think the answer should be and why. So you have 2 points that define a unique line, meaning like if I have 2 points on a graph, I can draw only one line that goes straight through them. So I'm curious to know how many points you need in order to define a unique parabola. So, if I have 2 points, I can draw this parabola between them. Is that the only parabola that could work? And so if that's the case, then you've found a unique parabola. I'm curious to know how many points you need to make it unique, meaning that's the only parabola that could go through those points. So let's go on to the lesson. So we've got our SWBAT for today, which is performing operations with complex numbers, finding absolute values of complex numbers, and then graphing them. So we're expanding our knowledge of complex numbers a bit today. Alright, so first we have to figure out what the complex plane is. Usually we're used to the coordinate axis, the coordinate plane, which has x and y on the axes, but if you're trying to graph complex numbers, you need something that deals with the imaginary part, because x and y, those are all real numbers, and so you can only plot real numbers. So we're going to actually jump to a completely new coordinate system, which is called the complex plane. And so instead of having x on the horizontal axis, we have our real numbers, and then we have on the y-axis our imaginary part, or our imaginary numbers. So I'm going to go ahead and label some of the values here. So it looks pretty similar to our regular coordinate system, except now instead of being able to plot a point xy, I can only plot one complex number at a time. And so the way you do that is you look at, for example, this first one, which is 2 minus 3i. And so the real part is 2. So that's how much you go over on the real axis. So I'm going to go over 2 on the real axis. Okay, and then it says minus 3i. So that means I need to go to negative 3 on the imaginary axis, because that signifies I'm at a negative 3i. And so that is the point 2 minus 3i. So it's not really a coordinate, right, because you don't have a x value and a y value. You're just plotting one number on this axis, or on this coordinate plane. So for number 2, negative 4 plus 0i, that has a real part of negative 4, so I'm going to go over negative 4, and then there's no imaginary part, so it's actually just on the real axis. So that's the point negative 4. 2i, there's no real part, but there's an imaginary part, and that's at 2. So that's going to be the point 2i. And then negative 1 plus 2i, I go over negative 1, and then positive 2i is right there. So that's number 4, which is negative 1 plus 2i. Not too bad. Just a different thought process. Alright, so the next thing we're going to talk about is the absolute value of a complex number. Now, for normal numbers, real numbers, the absolute value is defined as the distance from 0. It's still exactly the same definition, except now instead of being on the real axes, x and y, you're on the coordinate plane, the coordinates with real and imaginary parts. So you're still looking for your distance from 0, which is this point in the center. So if you're taking the absolute value of a plus bi, It's the distance that that point is from 0, 0 on the complex plane. Okay? And so let's actually take a look at what that means. So if this is my complex plane, I've got my real part and my imaginary part, sometimes shorthand written as RE and IM. I have, let's say I'm looking at the absolute value of, well, the first example, 3 plus 4i. Okay. The point 0, 0 is that one right in the middle. And then the point 3 plus 4i is I go over 3 on the real axis and then up 4 on the imaginary axis. So there's that point there. And so I want to know the distance between those 2 points. And so that would be this distance here. Now this is strongly related to something that you learned last year, which hopefully you're kind of looking at right now as the if I want to find this distance, right, I'm going to need to find use the Pythagorean theorem to figure out what that is, because I know this side is 3 and I know this side is 4, so then I'm going to need to figure out what this distance is, and because it's a right triangle, I'm going to do a squared plus b squared equals c squared. So I have 3 squared plus 4 squared equals whatever my c is, or my distance between those 2 points. And so I get 25 equals c squared, which means c has to be plus or minus 5. And since we're talking about the distance between 2 points, we can never have a negative distance, and so we take away the negative answer, and we know that the absolute value of 3 plus 4i is 5. Alright, so I've just written this down again. 3 plus 4i equals 5, because 3 squared plus 4 squared equals 5 squared, or 5 equals the square root of 3 squared plus 4 squared. And so that's using the Pythagorean theorem. You can do the same thing for this next example. Find negative 2 plus I. So you'd graph it again, and you say, oh, okay, negative 2, that's on my real axis. I'm going to the left 2, and then up 1. So that's my point, negative 2 plus I, and I want to find that distance between those 2 points. And so between that and 0, 0. And we can do the same thing. We can make a right triangle and try to figure out this side length. And we know that this is 2, this is 1, and so I know that 2 squared plus 1 squared should equal c squared, or take the square root of that, and that's going to get me my distance between those 2 points. So square root of 5. The distance, or c, equals the square root of 5, which means that the absolute value of negative 2 plus I equals root 5. Not too bad. Okay, so it's always going to work like that. Alright, next is adding and subtracting complex numbers, which is really, really, really easy. All you have to do is combine like terms. So let's look at these 2 examples. You can actually try them on your own first if you want. Shouldn't be too bad. We literally just combine like terms, and then you want to end up writing it in the form a plus bi. You don't want to have more than just 2 things, a real part and imaginary part. So in this first example, I've got 3 plus 4i plus negative 2 plus I. And so I can combine my real parts. 3 plus negative 2 is 1, and then I have a 4i and an I, and that's a 5i. So my final answer is 1 plus 5i. Not bad. Just be careful with a subtraction problem, because if you're subtracting the entire thing, that negative has to be distributed. So I've got 5 plus 2i minus 2, but I also have minus a negative 3i. So that's going to turn into a plus 3i, because minus a minus is plus. So again, combine like terms. I've got my real parts are 5 and negative 2, so that's 3. And then I've got 2i plus 3i plus 5i. Voila! Yay! We can add and subtract complex numbers. Good job. What about multiplying, you ask? Oh, great question. Super easy, something you also already know how to do. Now, since I've got this 3 plus 4i and this minus 2 plus I can't just multiply, I don't know, the 3 and the negative 2 and the 4i and the I, because I have a lot going on here. This is very similar to something like 2x plus 1 times x minus 5, where you have to FOIL everything, because PEMDAS tells us that we can't add before we multiply, right? So we have to FOIL. We have to do 3 times negative 2, which is negative 6. That's first. Our outer is plus 3 times I. Our inner is 4i times negative 2, which is minus 8i. And then my last is 4i times I, which is 4i squared. Okay. Now you can remember that I squared is equal to negative 1. Which means I can simplify this a little bit, and I've got negative 6 plus 3i minus 8i, so that's going to be minus 5i. And then I have plus 4i squared, or 4 times negative 1, which is negative 4. So I've got negative 6 minus 5i minus 4, and that's going to end up simplifying to negative 10 minus 5i. And we have successfully multiplied out these two complex numbers. And last but not least, we have dividing. Okay, now dividing is the one that's a little weird. So let's take a look at it. We've got 3 plus 4i divided by negative 2 plus I. I want you to remember, here's our little side note for a second. I want you to remember that a complex conjugate, right, is the complex number that changes the sign of the I. So the complex conjugate of negative 2 plus I is negative 2 minus I, right? These two are complex conjugates of each other. So you're going to need that for the next couple minutes. So the really cool thing about complex conjugates, and the reason why we teach you about them, is because they really conveniently cancel each other out. You end up getting rid of the imaginary parts, and so when you're dividing numbers, we don't like to have imaginary numbers in the denominator. So when we divide, basically we want to get rid of the complex numbers, and the complex conjugate does that for us. So if I take this problem, which is the same as the one that's written above, just written differently, right? I've got 3 plus 4i divided by negative 2 plus I. If I multiply by 1, I haven't changed the problem at all, right? So instead of multiplying by 1, just that number, I'm going to multiply by a special form of 1. So I'm going to multiply by the complex conjugate over itself, because anything over itself equals 1. So negative 2 minus I is the complex conjugate, but I have to multiply by it over itself, so that all I'm doing is multiplying by 1. So I haven't actually changed the problem at all. And remember that when you multiply two fractions together, right, all you do is you multiply straight across the numerator and multiply straight across the denominator. So it's super easy. All we have to do is write it out as like a problem like this: 3 plus 4i times negative 2 minus I all over negative 2 plus I times negative 2 minus I. And then I can just FOIL that out so that it looks nice and pretty. I've got 3 times negative 2, that's negative 6, outer is negative 3i. Inner is negative 8i. Last is negative, is 4i times negative I, which is a negative 4 times I squared. We'll simplify that later. Then we do the same thing to the bottom. Negative 2 times negative 2, positive 4. Negative 2 times negative I, that's positive 2i. Inner is I times negative 2, so that's a minus 2i. And I have I times negative I, which is negative I squared. So something to look at and to note is that here in the bottom, where I multiplied a number times its complex conjugate, I've got 2i minus 2i. And so that cancels out to 0. And that's actually why we multiply by the complex conjugate, because it gets rid of the imaginary parts in the denominator, because those two are always going to cancel out. So let's simplify this a little more. In my numerator, I have negative 6, and I've got minus 3i minus 8i, so that's negative 11i. And then I have minus 4i squared, or negative 4 times negative 1, which is a positive 4. In the denominator, my 2i and my negative 2i canceled, and then I've got 4 minus I squared, and I squared again is negative 1, so I'm subtracting negative 1, which becomes a 4 plus 1. I've got negative 6 plus 4, that's negative 2, minus 11i, all over 5. And then if I want to write that as a plus bi, I can just write it as negative 2 over 5 minus 11 over 5i. And then we've successfully completed this division problem. And so our answer is negative 2 over 5 minus 11 over 5i. Ta-da!